Good afternoon. Welcome back to Machine Learning by NSR Programmer. Yeah. So yesterday we looked at k-means clustering. And today we're going to dive into principal component analysis. So dimensionality reduction with principal component analysis. So in this tutorial we'll learn about dimensionality reduction, which is a crucial technique to simplify complex datasets while retaining important information. Our primary focus will be on the principal component analysis, or what people normally call PCA, which is a popular linear dimensionality reduction method. We'll start by, of course, defining some key concepts and definitions. We have what we call dimensionality, which I've just been talking about. This dimensionality is the number of features or variables in a data set. High dimensionality can make analysis difficult, and then if it's low, it's a bit easier. Then we have dimensionality reduction. This is the process of reducing the number of variables under consideration while preserving as much information as possible. And then our focus of today, principal component analysis, PCA, is a statistical procedure that transforms original correlated variables into a smaller number of uncorrelated variables called principal components. Then we can define what principal components are. These are the new features created by PCA that capture maximum variance in data. Then to define what variance is the measure of spread or dispersion of data points in a feature. And eigenvectors and eigenvalues. In PCA, eigenvectors define directions for principal components, and eigenvalues are their magnitude or the captured variance. Then we have what we call explained variance ratio. This is the proportion of the dataset's variance captured by each principal component. And then we have a term called whitening. This is like optional PCA, an optional PCA variant that scales components to have unit variance, so it decolorates variables. So after defining that, then now we can look at our example demo of a PCA on an iris dataset. Of course, we'll start by importing all our necessary inputs or libraries, sorry. Okay, so this is a simple script. It's not long, so let's break it down line by line. Of course, from the first line to the fourth line, those are the necessary libraries that we import. NumPy for providing support for arrays, matrices, and numerical computations. Matplotlib library for making charts or visualization. scikit-learn dataset imports a function to load the iris dataset, which I've said over and over again. The iris dataset is a classic dataset for machine learning examples. And then line 4, the decomposition. Import PCA. It imports the PCA class from the scikit-learn decomposition module to perform principal component analysis, which we are looking at today. And then line 7, that line loads the iris dataset into the variable iris. Iris is a structured object containing feature data, labels, and metadata. Then line 8, x iris data extracts the feature matrix X, which is a 2D array where rows are samples and columns are features. For example, simple length and petal width. Y, that's line 9. Yeah, line 9. Y is equal to the iris target. It extracts target labels. Y indicating the species for each sample, 0, 1, or 2. And then feature names, line 10. That says human readable names of the dataset features for potential use in labeling. Then line 11, excuse me. Line 11 stores the species names. Setosa, versicolor, genica, for plotting and interpretation. And line 14, PCA is equal to PCA and component is equal to 2. That creates a PCA object that will reduce input features from 4 dimensions down to 2 principal components. So this n component is equal to 2 specifies the dimensionality of output space. And then line 17, that fits the PCA model on the full data matrix X. Yeah, to learn principal components, then transforms X into a new matrix X dash PCA, representing samples in the reduced to D space. In line 20, that prints the fraction of input data variance explained by each principal component. For example, if it's 0.92 and 0.05, means the first component accounts for 92% and the second for 5% total. Like, let's say if it was like this. Yeah. So the first component here accounts for 92%, and the second one for 5% of the total variance. So that's what we expect to see, something like this when we run the script here in the terminal. These are the results, something similar like that. And then of course we start to plot the first two principal components. Line 23 creates a new figure window for plotting with a specified size. Line 24 defines colors for each iris species to distinguish them visually in the plot. And then line 25 to 26, so for each class or species, it plots a scatter plot of the samples projected onto the first two principal components with the corresponding color and label. And that's all in here. And then of course the legend method is using the species names to identify clusters in the plot. And then of course the labels, the x-axis and the y-axis of the plot corresponding to the first and second principal components. And then of course the title, and then this will display the plot. So in summary, what this code is doing is it applies the PCA or principal component analysis to the iris dataset which we loaded to reduce the original 4 features per sample into just 2 principal components. It then prints the proportion of variance captured by these components and plots the samples in this reduced 2D space colored by species. So it helps visualize how well PCA can separate the classes in fewer dimensions, revealing underlying structure while simplifying the dataset. So I'm going to run the script now. Okay, I can see the stream is a bit behind, but I've got the results here. So let me first minimize the plot. So yeah, so this is the explained variance ratio. So the numerical output is showing the percentage of total variance preserved by each principal component. So high values for the first component, yeah, you can see this is 92%, point something, yeah. So high values for the first component indicate successful dimensionality reduction with minimal information loss. So the first component is 92%, and then yeah, this one is 0. 0 is 5% rather, 0.05. So that's our terminal results. Let me maximize this again. The plot. So yeah, this is our 2D plot. The scatter plot is a 2D plot showing the transformed data points. The different colors represent different iris species, allowing you to visually see whether PCA helps distinguish these classes based on condensed features. So we have Setosa, versicolor, and virginica. Those are our 3 species. Yeah. So that's how PCA is done in machine learning. So, of course, don't forget to check out the repo as I push this file. Thank you for tuning in once again. Don't forget to like the video, share it with friends, leave a comment, and subscribe to the channel. Have a blessed evening.